We're going to be doing 4-4 today on exponential and logarithmic equations. So we're going to use like basis to solve exponential equations, then logarithms, and then we'll use the definition of a logarithm to help us solve logarithmic equations. Then we'll learn the one-to-one property, and then solve applied problems involving the exponential and logarithmic equations. So this first one is going to be when you want to solve exponential equations where you can make the numbers have the same base. So you can see here that I was able to write them both with the same base. So if the bases are the same, and we're saying that these are equal to each other, then that would mean that m and the n are equal to each other. So that's how we get this. So the first thing you want to do is try to rewrite the equation in the form where they have the same base, and then set m equal to n, and then solve for the variable. Okay, so for example, this one we have a base of 2 and a base of 16. Now we know that the number 16 can be written with a base of 2 because we can write it as 2 to the 4th. So now I'll write 2 and then bring down the 3x minus 8 that we had. So now that the 2's are the same, we can set this equal to this. So we have 3x minus 8 equals 4. Then we add the 8 to get 3x equals 12. Divide by 3. So x would equal 4. So if you want to see if you did this right, you could plug it back in for the x. I'll check it right here. And I'm saying 2 to the 3 times 4 minus 8 should equal 16. So if I do 3 times 4, that's 12 minus 8. So that's 2 to the 4th equals 16. So that checks out. Okay, let's try this next one. Letter B, we have 27 and x plus 3, and then 9, x minus 1. So your first question you want to ask is, can I write 27 with a base of 9? No, you cannot, because if you did 9 to the first, that'd be 9. 9 to the second is 81. But hopefully you recognize that these can both have a 3 divided out of them. So this is the same as 3 to the third. Then we'd have the x plus 3 exponent. And then 9 can be written as 3 to the second. So now they do have the same base. And now through the power property, we can do some distributing here, because we can multiply a power by a power. So that would be 3 times x. It's like we're doing distributive. 3 times x is 3x. 3 times 3 is 9. And same here, I can distribute the 2. So I'd have 3 to the 2x. And then 2 times negative 1 is negative 2. Okay, so now that my bases are the same, I can go ahead and move forward. So I can compare this with this. 3x plus 9 equals 2x minus 2. Get my x's together. So that'd just be 1x plus 9 equals negative 2 minus the 9. And I'm going to get x equals negative 11. Okay, so if you wanted to double check this, you would put this negative 11 in for both x's and see if you get both sides to be equal to each other. And 1b is just some step-by-step examples that you can look at on your own. Okay, now this is convenient if they can both have the same base, but most exponential equations can't be written so that each side has the same base. So here's an example. If I have 4 to the x equals 15, you can't rewrite 15 to have a base of 4 or a base of 2. And with our 10 to the x equals 120,000, you can't rewrite 120,000 to have a base of 10. So this is where logarithms come in. So if m equals n, then the log of b with an m is equal to log of b with an n. So if the equation involves base 10, we're going to take the common algorithm on both sides. Any other base, we're going to take the natural logarithm of both sides. So this is the main thing you're going to want to take away here. So we'll use that to help us on the next slide. So first you need to isolate the exponential expression. So get the exponent on one side. Then take the common logarithm on both sides if it's a base 10. Take the natural logarithm on both sides for bases other than 10. Then we're going to simplify using one of the following properties. So the natural log of b to the x is the same as x to the natural log of b, and that was that where you could move the x down in front. Or the natural log of e to the x is equal to x. Or the logarithm of 10x equals x. So these you're going to want to memorize these three. This one, and this one. That will help us. And then you'll be able to solve for the variable. Okay, so let's go ahead and try those two that we said can't be written with the same base. So we have 4 to the x equals 15. Okay, so these do not involve a base of 10, so we're going to have to do the natural log. So we're going to take the natural log of both sides. So we have natural log of 4 to the x and the natural log of 15. So we're just applying the natural log to both sides so that it remains equal. Okay, let's go ahead and drop this x down front. And the right side stays the same. So now we're trying to solve for the x. Trying to figure out what would this x be right here. So now I can just isolate the x by dividing by the natural log of 4. So now those cancel and I'm left with x equals the natural log of 15 over the natural log of 4. So sometimes it'll say what's the exact answer, you would leave it like that. Now if you want to see if your answer would make sense, let's go ahead and plug this into your calculator. This is going to give you about 1.95 for x. So that would make sense because let's think of what we do know. We know that 4 to the first is 4, and we know 4 to the second is 16. So to get 15, it had to be really close to 4 to the second. So 4 to the about 1.95 gives you the answer of 15. So it's always good to plug in the calculator just to see if your answer does make sense. Okay, on this next one, we do have a base of 10 involved. So we can go ahead and use a logarithm. So log 10x, and then multiply the other side by log. So now, log 10 to the x, we said is the same as x, and the log of 120,000, we'll just leave it as that. There's nothing I can simplify there. So now the x is already isolated, so now we're just going to plug this into our calculator, or you can leave it like this if they want an exact answer. So if you plug it into the calculator, you should get that x is about 5.08. Okay, so let's see if this would make sense. So I know 10 to the third is 1,000. 10 to the fourth would be 10,000. 10 to the fifth is 100,000. So 10 to the 5.08 is going to be a little above that, so about 120,000. So that would make sense. And here's another one you can just look at on your own for an extra example. Okay, now this one has a little more involved. We have 40 times e to the 0.6x minus 3 equals 237. So we notice that there's too much going on with the left side. We have to have the exponent isolated. So first we're going to add the 3. We're left with 40 e to the 0.6x equals 240. And then we can divide by 40 to get e to the 0.6x equals 6. Okay, so now we're going to take the natural logarithm. We don't have any base of 10 here, so let's go ahead and multiply both sides by the natural log. Just squeeze it in front here. So now the natural log of e to the 0.6x, the natural log of e just becomes 1, so that becomes just 0.6x equals the natural log of 6. Now to finish solving for x, we'll divide by 0.6. So we have x equals the natural log of 6 divided by 0.6. So if I want exact, you could write this. If you want a decimal approximation, you plug that in your calculator, you get about 2.99. And you could go ahead and plug that back in for the x up at the top and see if you get something that equals 237 at the end. 3b, there's a base of 10 example that you can look at on your own. Okay, example 4a is 5 to the x minus 2 equals 4 to the 2x plus 3. So neither of these have a base 10. We can't write them with a common base. So let's go ahead and take the natural log of both sides. Now we can go ahead and bring this whole quantity down front. So you want to make sure you put in parentheses because it's that whole quantity being moved out in front to be multiplied. Same with this side. Next, we're going to go ahead and distribute this through. And it's going to be easiest if you put the x out front. So x times the natural log of 5 minus 2 natural log of 5. And then same here. We'd have 2x times the natural log of 4 plus 3 natural log of 4. Next, we're going to rearrange this to make it simpler. So we're going to move the x over with this side and move this one over here. So we'd have x natural log of 5. Then I have to subtract the 2x natural log of 4 to get to the other side. Then if I add this one over to get it to move, I'd end up with a positive 2 natural log of 5. And then I still have this over here plus 3 natural log of 4. Okay, and the reason we did that is because now I can pull the x out of both of these. So if I factor the x out, I'd be left with the natural log of 5 minus 2 times the natural log of 4. And the other side I can't factor anything out, so I'll just rewrite it. And our final step, we can go ahead and divide by this whole thing, the natural log of 5 minus 2 natural log of 4, because that's going to get this to cancel, so the x is by itself. But I have to do it to the other side as well. And there's actually nothing else I can do there. So this is my final answer. The x is going to equal. And then if you plug that in your calculator, you're going to get that x is about negative 6.34. And there's another good example you can look at here on 4B on your own. Okay, so now we're going to use the definition of a logarithm to solve logarithmic equations. So first you're going to want to try to express it in this form here. Use the definition of a logarithm to rewrite the equation in exponential form. So this, we learned, is going to mean the same thing as b to the c equals the m. So b to this exponent equals the m. Then you'll solve for the variable and then check your solutions in the original equation. Include in the solution only values where m is greater than 0. Okay, let's go ahead and try this one. So you notice here that we have a quadratic equation. We have 3 terms, so it's a trinomial, and then we have a squared term here. So let's ignore the exponents for now and just look if this was just e minus 4e plus 3, where you can look at these numbers. We're trying to find factors of negative 4 that will add to positive 3. So we're going to use negative 1 and negative 3. So this whole thing can be written as 2 binomials. We'd have e to the x minus 3 and e to the x minus 1. You can always distribute that out and see if you end up getting this original, but you will. Okay, so now we can set both of these equal to 0. So we'd have the first one equal to 0, and then the second one equal to 0. Go ahead and solve it. We isolated the exponent. So now we can multiply both sides by the natural log. Okay, so we know the natural log of e to the x is just x. And then we'd have the natural log of, sorry, this should be an e right, or a 3 right here. Natural log of 3. So there's one solution. And let's go ahead and solve the other one. Add the 1. Multiply both sides by the natural log. Okay, so this just becomes x, and the natural log of 1 is 0. And if you want to try this in your calculator, this is about 1.10. So you could plug both of these back in for the x's in the original, and you should get an answer that comes out to be 0 at the end. So our solution set, we're going to say is 0, and then we'll write the original natural log of 3. Okay, the example 6, we're going to have a logarithm involved in this one. So a few slides ago we said to remember that log b m equals c means b to the c equals m. So using that, this is my b, this is my c, this is my m. So I can say 4 to the second equals x plus 3. So that's 16 equals x plus 3 minus the 3 over. That means 13 equals x. Now we're going to check this to make sure it works. So if I have log of 4, I replace the x with a 13 plus 3 equals 2. Log of 4, and then that would be 16 equals 2. This should be true because you would get 2 equals 2 if you tried this in a calculator. Or we know that 4 to this power should give us 16, and it does. So it checks out both ways. Okay, 3 times the natural log of 2x equals 12. So first let's divide both sides by 3 to try to simplify it down. Okay, so next we're going to rewrite this as the log with base e. And then we'll just rewrite everything else. We have 2x behind it equals 4. So then we said that b to the c equals m. So we can say e to the 4th equals our 2x. But then we'd still have to divide by 2 to isolate the x. So that means x equals e to the 4th divided by 2. Okay, let's go ahead and check this one. So we're going to plug it back in for x here. Okay, so my 2's cancel, so I'm left with 3 times the natural log of e to the 4th equals 12. We want to know if this is true. So we'd have this simplifies to 4 times 3 should equal 12, and it does. 6c is one you can look at on your own for an extra example, and same with 6d. Okay, now we're going to solve logarithmic equations. Okay, so we learned in a previous lesson that when you see this plus sign, this is the product rule. So we had learned that log of b to the m, b times m, and then the same thing with an n, can be written as the product of the m times the n. So we're going to use that to help us rewrite this. So we would end up with log of 2, then multiply this and this, because this would be my m and this would be my n. Equals 3. And now we can use our b to the c equals m to help us. So we'd have 2 to the 3rd equals this whole quantity, x times x minus 7. Let's go ahead and multiply that out. So that would simplify to 8 equals x squared minus 7x. Let's move the 8 to the other side. We'd have 0 equals x squared minus 7x minus 8. And we can factor that to be x minus 8 times x plus 1 equals 0. So I'd have x minus 8 equals 0, or x plus 1 equals 0. Therefore, x can be 8, and x can be negative 1. And then we're going to check these on the next slide to see if they are true or not. Okay, so we had these two solutions. So we're going to check them. So the first one, we're going to plug it in for the x. So that gives us log 2, 8 plus log 2, 1 now. We want to know, does that equal 3? Is this true or not? So in our last lesson, we talked about how you could plug this into your calculator. One way would be to write this as log of 8 divided by the log of 2. You're going to end up getting the number 3. Then plus the log of 1 divided by the log of 2. That's going to give you 0, which does equal 3. So this one does check out. Okay, let's go ahead and check negative 1. So I'd have log 2 and replace the x with negative 1. Replace this x with a negative 1. Does this equal 3 is what we're trying to find. So log of 2 to negative 1 plus log of 2 negative 8. And we had said that this right here, the m, has to be greater than 0. So this one, negative 1, does not work. The domain of a log function is only positive numbers. And 7b is another step-by-step one, and it also shows you how to check it on the next slide. So I encourage you to look through those examples. Okay, now using the one-to-one property, so we're going to express the equation in this form, and this form involves a single logarithm whose coefficient is 1 on each side. Use the one-to-one property to rewrite the equation without logarithms. So we know if this is true, then m is equal to n. Solve for the variable. Then we'll check our solutions in the original equation and include in the solution set only values where m is greater than 0 and n is greater than 0. Okay, so on this one we can see that we have subtraction involved. So we can apply the quotient rule. So this can be rewritten as the natural log of x plus 3, or 2, divided by 4x plus 3. And keep the other side the same. Now we can use the one-to-one property, and pretty much these, we don't need them anymore. So we'd have just x plus 2 over 4x plus 3 equals 1 over x. And now we'd have to try to solve for the x. There's a couple ways to do this. What I'm going to do is try to get this x out of the denominator. So now we have 1 on that side, and then we'd have x times x plus 2 over 4x plus 3. So now I need to get that out of the denominator, so I'm going to multiply by 4x plus 3 on both sides. So now I'd have x squared plus 2x after I distribute equals 4x plus 3. Let's go ahead and move everything together so that we can try to simplify it. I'm going to move this over and this over. So I'd end up with x squared minus 2x minus 3 equals 0. And we can rewrite that as x minus 3 times x plus 1 equals 0. Meaning that my two answers would be positive 3 or negative 1. And then we're going to check those to see if they both work or if one of them works on the next two slides. So let's go ahead and check x equals 3. So I have natural log of 3 plus 2. I'm just replacing all of my x's here. I said natural log of 4 times 3 plus 3 equals a natural log of 1 over 3. So I get natural log of 5 minus, this would be 12 plus 3, so the natural log of 15 equals the natural log 1/3. So we can rewrite this using the quotient rule. So we'd have natural log of 5 over 15, which would reduce down to the natural log of 1/3. So we have the natural log of 1/3 on both sides. So x equals 3 does work in this situation. If I try this one, I'd have natural log of negative 1 plus 2 minus natural log of 4 times negative 1 plus 3 equals a natural log of 1 over negative 1. So either way, we're going to see we're going to get a lot of negatives. So that's negative 4 plus 3 is negative 1. So we can't have logarithms of negative numbers. So x equals negative 1 is not going to be one of our solutions. And then 8b, there's 3 slides here where you can check this one and see how they did it step by step. Okay, and just an application problem couple to end with. So the percentage of adult height attained by a girl who is X years old, that's what the X stands for, can be modeled by f of x equals 62 plus 35 log x minus 4, where x represents the girl's age from 5 to 15, and f of x represents the percentage of her adult height. At what age will she get the 97% of her height? So this One, we know that we're trying to get to a 97. And we're going to go ahead and solve this. You end up simplifying it down to this. Remember that there's like an invisible 10 if there's no number down here. So you could say this 10 to the first power equals the other side because of that b to the c equals m property. And if you end up solving that out, you get x equals 14. So at age 14, a girl has attained 97% of her adult height. And our last slide, how long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? So that would mean a 4 for the n. So we're going to start by just plugging everything we do know. We know we're trying to get to 3,600. We know we started with 1,000. We know the interest rate is 8%, and we know the n is 4 on the top and the bottom. So we're going to simplify as far down as we can. Once we get over here, we need to go ahead and take the natural log of both sides. And then we bring this 4t down front. And then we solve for t by dividing by this whole thing here to get this t all by itself. So you end up with natural log of 3.6 divided by 4 times the natural log of 1.02 equals 16.2. So at 16.2 years, that was our t. 1,000 will grow to 3,600. Okay, and that is the end of this video.